Okay, guys, so today we're doing chapter 2, the kinetic theory of gases. And here's what we're doing. So this is sort of one of the important relationships we'll be deriving. Oops, where is it? Okay, so here's a relationship we'll derive. Okay. Now, before I go into this, well, okay, so let's talk about this. What this tells you is this is the pressure that the gas is exerting, and the pressure that the gas is exerting is related to this term. You can see that what is this expression? It's kinetic energy. It's the kinetic energy of a single molecule. Okay? Do you guys know what is atmospheric pressure? What is the value for atmospheric pressure? Go ahead. Take a guess. What's atmosphere? Huh?
1 atmosphere.
Oh, that's like saying I'm living next to my neighbor. That's not saying. Yeah, no, it's not wrong. Yeah, you're living next to your neighbor is not wrong. Yep.
Is it like 800 pascals?
No, it's 100,000 pascals. Okay. 1 atmosphere. So 1 atmosphere is 15 psi. What does psi mean? Pounds per square inch. Okay, so roughly here is a square inch, right? So what does this mean? That air is pushing the square inch with a force of 15 pounds. Again, this sheet of paper is 10 inches by 10 inches, 100 square inches. So air is pushing this paper with a force of 1,500 pounds. 15 times 100 is 1,500. Air is pushing this piece of paper with a force of 1,500 pounds. Yep.
Why is there no interactions? Is there like a normal pressure pushing back?
So yeah, why is it? So that was the next question, and you sort of answered it back. It's pushing it equally back with 1,500 pounds. Okay. How's the air exerting that force? So here are these air molecules bouncing off, and billions of them are hitting every square inch every second, and that's exerting the force. Do you feel any of the air molecules bouncing off of you? So billions and billions of them are colliding every second and exerting that force. Okay? And so that is what this relationship is saying. Okay? So the idea is to derive a macroscopic property. Here's something that you can measure using a handheld instrument. So that's what we mean by a macroscopic property. We are relating that to a microscopic property, something that you don't feel and see. Okay, so that's the big deal in this chapter. Okay. Now this 1,500-pound force that I talked about, let me demonstrate that to you guys. Okay, this is real.
Real funny.
Yeah. So I'm going to try and break this here. Okay. Some of you've seen this before. So, will it break? So what are we trying to do? We're trying to demonstrate that 1,500 pounds. Okay? Mooney, come over here. Well, no, actually not. Austin. I dropped him more. Stand over there. Okay. So now push down on that hard. Okay, like that. Right there, too. Well, I guess you gotta come this side, you're blocking everybody's view. All right, now we'll try the same thing. Okay. Of course it breaks, right? Well, did you guys see that? All right. We'll do the same thing. There's the 1,500 pound. Okay. Right now, there is air underneath it too. I mean, so there's sort of air underneath it too, and that's balancing it. Now, when I hit this, the paper will rise. There'll be a vacuum underneath the paper, and you'll get the 1,500 pounds. Okay? All right. So that's my favorite demo. That was in the Scientific American, and it's cheap and it freaking works every time.
Not last time.
Well, last time we used a pencil and Winnie was assisting. And all right, so that's what we're doing in this chapter. Okay, so the kinetic theory associates macroscopic properties to microscopic properties. Okay, so this is saying the pressure exerted by the gas is from all these air molecules bouncing off, and billions of them are bouncing off. So even though you don't feel an individual molecule colliding with you, you do feel the collective effect. Okay, right. So that's what we're going to derive, but we'll talk about other stuff too along the way. See, I mean, those ideas just don't develop overnight. They're a culmination of 200, 300 years of ideas. Okay, I mean, they're a culmination of ideas that developed over 200, 300 years. Okay, and so we'll talk about that. So people started. So again, that's the kinetic theory of gases. It's a theory that relates microscopic properties to macroscopic properties. Look at her teaching, throwing stuff at the teacher. So we want to go from microscopic properties to macroscopic properties. Okay. All right. So people started experimenting with gases a while ago. And today, I mean, the day you're born, you see this expression. Yeah. What is this? This is the ideal gas. You didn't see that? Mm-hmm. You didn't see that? Yeah, see, I knew that. I knew that. So.
Now you calling me out, man. That's Winnie, not me.
Oh, no. Winnie is a constant background. I'll keep picking on. But.
That's how I feel about your class.
So this thing you guys see, I mean, at a very early stage these days, but this thing developed over 200 years or so. Okay, so Mr. Boyle was investigating gases, and here's what he discovered back in 1662. That's almost 350 years ago. That if you hold the pressure and volume, what he found was if you hold the temperature constant, for a given amount of gas, so this guy is constant. Pressure and volume are inversely related. Okay, pressure and volume of a gas are inversely related. So what he found was, of course, he didn't know this expression. What he found was if you increase the volume, the pressure decreases, or if you increase the pressure, the volume decreases, such that the product remains constant. That's what he found. Okay, back in 1660. So that he found one piece of that law. Then 100 years later, Mr. Charles stated that at constant pressure, the volume of a gas is proportional to its temperature. So what 100 years later, Mr. Charles found that if you hold the pressure constant, this is constant now, if you double the temperature, the volume doubles. Okay? So we are still unaware of this formula for 120 years. We were discovering piecemeals of it. And what allows that? What allows that kind of discovery? It's the available technology. Okay? So what you want is, so to discover this law, what would you need? So you want to hold a constant pressure meaning, let's say you have some kind of container, the pressure on it is atmospheric pressure. You raise the temperature of that, its volume needs to increase without any air leaking. So that kind of, you needed that kind of technology to discover that. Okay? Something that's expanding without letting air leak. Even today, you probably couldn't have that without letting helium leak. If you have small molecules, you probably can't have a container that would not allow helium to leak. Okay. Anyway, so Mr. Charles discovered that. Okay. And in 1800, so another 15 years later, Gay-Lussac found that when a volume of the gas is held constant, its pressure is proportional to temperature. So you double the temperature, pressure will double if the volume is held constant. Okay. Then in 1811, Avogadro found that the ratio of the volume of number of particles is constant if pressure and temperature are constant. Okay. So what Mr. Avogadro found was, you hold the temperature and pressure constant, you double the amount of gas, the volume will double. Okay. So if you had 100 molecules, and now if you have 200 molecules, the volume will double. That's what we want. Okay. And then, so now you can combine all these laws and come up with this equation. Okay. So all these laws are stating that equation, and that's the ideal gas law. So the ideal gas law that you're so familiar with was put together over 150 years. Okay. Now here's a great way to look at it. Here's a modern way to look at it. Okay, so you have this gas, and what are the properties you're changing? You are making any changes to the gas. What you end up doing is, let's say, you gather all your physics books and burn them here. What will happen? You're adding energy to the system. Okay, you're raising its temperature and pressure. So no matter what you do to the gas, as long as it's not leaking out, for a given amount of gas, these values are on this surface. Okay, so for no matter what you do to this, for a given amount of gas, all you're doing is moving along the surface. So the pressure, volume, and temperature are on that surface. Okay. You change the amount of gas, the surface changes, that's all. If you increase N, this surface goes higher. Okay. So now the way to look at it, so this is the surface on which your gas is living. So what did Mr. Boyle discover? He discovered a constant temperature law. A constant temperature is this slice. You take a slice perpendicular to the temperature axis. Okay? And he's discovered that slice. What he found was, as you increase the volume, the pressure is decreasing such that their product is constant. What does Mr. Charles discover? He's holding the pressure constant. So he's taking this slice perpendicular to the pressure axis. And he's discovered that slice of the surface. Okay? So if you hold pressure constant, you increase the temperature, volume increases. So here's Mr. Charles, pressure slice. You increase the temperature, the volume is increasing. Okay. Gay-Lussac's found that when the volume is constant, its pressure is proportional to temperature. Okay. So when the volume is constant, you're taking this slice. And as you increase the temperature, pressure is increasing. Okay. So that's the modern way of looking at it. Okay. And again, the important point here is we see these laws all the time, but they were put together over a long time. We'll talk about ideal gases. Okay, so all those laws apply to ideal gases. What ideal gases mean is that, so here are the assumptions for ideal gases. There's, how many gas molecules are there in this room? Air molecules are in this room? Austin, you don't remember the number? 10 to the power 28. 10 to the 28, okay? 10 to the 4 moles. So about 10,000 moles, and each mole is about 10 to the 24 molecules. So there's about 10 to the 28 molecules. Okay? And the assumption is, the molecules don't interact with each other only when they collide. The volume of, if you put together all the 10 to the 28 molecules together, they'll occupy a volume very small compared to this area. So the assumption really is that the volume is the volume for the gas to free run around it. Okay? That would not be true if you replace the gas molecules with ping pong balls. You couldn't fit 10 to the power of 28 ping pong balls in this room. Okay? Then the volume they take is comparable to this volume, and in fact larger than this volume. Okay? So anyway, the ideal gas laws, there's assumptions like that. So again, so for a given amount of ideal gas, every state of the gas is a point on this particular surface. So that's the, okay. Any process for a fixed amount of gas, any process, you can do anything you want. Okay, heat it, cool it, takes the gas from one point to another. Okay, so for instance, at constant volume, if you increase the temperature, you're moving the gas along that line. At constant temperature, if you're increasing the volume, you're moving the gas along that point. Okay. So there's the ideal gas law. You see it in two forms, PV equal to NKT and PV equal to nRT. Okay. In this formula, N is the number of molecules, and in this formula, little n is the number of moles. Okay. This is the Boltzmann's constant, and this is the gas constant. Okay. And so the Boltzmann's constant and the gas constant are related. It turns out that the gas constant is Avogadro's number times the Boltzmann's constant. Okay. And you guys have seen this before. 1 mole of any gas. So this is interesting. 1 mole of any gas. You could take hydrogen, helium, nitrogen, oxygen, any gas. At atmospheric pressure and 0 degrees Celsius occupies 22.4 liters. Okay. That's about 5 gallons. So 1 mole will occupy about this much. The top slice of this stick. All right, so here the ideal gas law in terms of the number of molecules. And there's the Boltzmann's constant, the subscript B being after Boltzmann, okay? And there's the value of the Boltzmann's constant, 1.38 times 10 to the 23. So all these macroscopic properties that you can measure using handheld instruments are called thermodynamic variables. Those are the variables you use to describe the state of the system. Okay. the mole is Avogadro's number, and again, as you all know, it's 6 times 10 to the 23 per mole. Okay. 1 mole is the number of atoms in 12 grams of carbon-12. Okay, so that's the definition. Carbon, that's the isotope you're going to take. So if you take 12 grams of this isotope, carbon-12 isotope, naturally occurring carbon has carbon-14 in it as well, a little bit. But, so if you take 12 grams of carbon-12 isotope, you'll have that many carbon atoms. Okay. So 1 mole of any substance stuff is that many. 1 mole of cars is that many cars. 1 mole of water molecules is that many molecules. Okay. So how much is 1 mole of water? What you do is you find its molecular weight, and molecular weight of water is 2 plus 16, 18 atomic units. That's the molecular weight. So if you take 18 grams of water, you have 1 mole of water. And you'll have 6 times 10 to the 24 molecules of water. Okay. So this diagram just gives you a feel for this number. This is an enormous number, a trillion. See, there is Mount Everest, which is 9 kilometers high. If you take a mole of ping pong balls, it would cover the whole Earth to that height. On a macroscopic level, Avogadro's number of table tennis balls would cover Earth to a depth of 40 kilometers. 4 times the height of Mount Everest. Okay, so here's the ideal gas law. This is assuming that the volume occupied by the molecules are negligible. They do not interact except when they collide and stuff like that. Okay. So, and this works great for the gas in this room for low density gases and stuff like that in low density situations. But if you're dealing with a very high density gas and a gas that is sort of interacting, here is the first order correction to that law. Okay. In this volume, that's essentially, remember, the volume for the gas to run around it. And this is true as long as the volume of the molecules is negligible. If it's not, you just subtract that volume. Okay. So this is related to the density of gas molecules, and this is a constant related to that. So the bigger the molecule, bigger B will be. Okay. So you're subtracting the volume of the gas itself from the total volume. So that's the correction. And you would need that for a high density gas. And if the gases are interacting, okay, so let's say, okay, so the pressure is exerted by these gas molecules bouncing off. But now if this guy is attracting that guy will hit the wall with a slower speed. Okay, so if there's an attractive force between the molecules, the pressure exerted by the gas will be smaller. Okay? And so you introduce that term, and again, that's dependent on density. When you add this term, this pressure has to be lower. Okay? So anyway, this is a correction. This is called the van der Waals equation, and this is a correction to this equation. In the low density limit, the terms containing A and B are negligible. In low density limit, these two are essentially 0. And then you come to that law. Yeah. So if you're having to use this equation, you've reached the big leagues. Okay. what are the molecules? What does air contain? What are the molecules, types of molecules in this room? Nitrogen and oxygen. So 78% nitrogen, 21% oxygen, and then 1% of the rest of the stuff. What is the pressure? 1 atmosphere. Yeah. And 15 psi and 10 to the power 5 pascals. So what Mr. Dalton realized was, okay, so the total pressure in this room is 1 atmosphere, and there are several gases in this room, and the total pressure is exerted by the individual gases. Okay, so the total pressure is the pressure exerted by nitrogen plus pressure exerted by oxygen and so on. Okay? And what he's saying in this equation is, okay, the partial pressure exerted by an individual gas is equal to the fraction of molecules that are in this mixture. Okay, so the pressure exerted by nitrogen is 0.78 atmospheres. The pressure exerted by oxygen, the fraction of oxygen molecules is 21%, so it's 0.21 atmosphere is exerted by oxygen. Okay. So what Mr. Dalton is saying, if you have 3 gases, one is 60%, 30%, and 10%, 60% of the total pressure will be exerted by that gas, 30% of the pressure will be exerted by this gas, 10% of that gas. Okay? And that's Dalton's law. Okay? So the total pressure is the sum of the partial pressures, and the partial pressure is just equal to the fraction of that gas times the total pressure. Okay. Okay. There's water vapor in this room. Okay. And so there's a vapor pressure, that is, water vapor is exerting a partial pressure. Okay. Now it turns out that, okay, so let's look at this table. Saturated vapor pressure. Okay, so this is saturated vapor pressure and density for water. What this is telling you, this table is telling you is at these temperatures, for in this room, the temperature is 20 degrees Celsius. What this table tells you is what the saturated vapor density. What do you think that means, saturated vapor density?
How much water vapor is in the air?
Okay, so that's the maximum water vapor it can hold. That's what saturated water vapor means, okay? And so let's look at this. At 20 degrees Celsius, it can hold 618 grams per meter cube. Here's a meter cube. 618 grams, a soda can is about 350 grams, so 2 soda cans worth of water. Okay, so that is the maximum water vapor that the air could hold at 20 degrees Celsius. Okay, and you can see that from this table, as the temperature rises, it can hold more and more water. As the temperature lowers, it holds less and less water. Okay. What happens? So let's do it this way. Okay. And this is called 100% humidity. If the air has 618 grams at 20 degrees Celsius per meter cube, then that's 100% humidity. What if the air has 309 grams per meter cube? That's 50% humidity. All right, so we live in Florida, we live in constantly 100% humidity. Okay? Let's do the following. Okay, so the temperature now is 220 degrees Celsius. That's the amount of water vapor. let's drop the temperature to 10 degrees Celsius. When does that happen? At night, the temperature drops. Or you can flip a switch too, right? Then you can do that. All right, at 10 degrees Celsius, the air is only supposed to hold, it can only hold 500 grams. But you started off with 600 grams. So what's going to happen now? That water has got to condense out. That's the dew forming. Okay? So any excess amount of water condenses off. Okay? All right. So if it has the maximum amount of water, what does that mean? No more water can be held there. You go for a run and you're sweating, and your sweat can't evaporate now because the atmosphere has maximum amount of water. Okay? And so high humidity that's why it's uncomfortable, because that's one of the ways you're air conditioning yourself. The water evaporates and then you cool down. Okay? So anyway, so that's the saturated vapor table. Okay, so it's a very useful table. And so this is the pressure at 20 degrees. The saturated vapor pressure is 2.33 times 10 to the 3. That is the saturated vapor pressure. 1 atmosphere is 10 to the power 5. So saturated vapor pressure at 100% humidity, it would be 2% of the atmospheric pressure. Okay? So that's what that is saying. All right, so now we're going to study the kinetic theory of gases. We're going to derive this relationship. Okay? P equal to, is it 2/3 N over V, 1/2 mv squared. Okay? Let's make sure the expression. Yeah. Okay, so this is the big deal, I guess. So here is a macroscopic quantity, something that you can measure using a handheld instrument, and you're relating it to something that you cannot see. Okay? You're going to relate it to the microscopic property of the gas. Okay? And that's the kinetic theory. So we're going to study ideal gases. Okay? So the goal is to relate macroscopic properties to the microscopic property of the gases. So here are the assumptions. The number of molecules is large, and that is true. The number of molecules in this room is 10 to the 28. They obey Newton's laws. They undergo elastic collisions. What does elastic collisions mean? Kinetic energy is conserved. Okay? So when they collide, they're not exciting each other and losing kinetic energy. So, yep.
For the equation you just had up there, what is the line over, what does that line mean?
That means average. So see in this simulation, are all the molecules moving at the same speed? All different. They all have different kinetic energy. So when you put the line, you're taking the average kinetic energy of all of them. Yep. So the collisions are elastic. Forces between molecules are negligible except during collision. So there's no force between them except when they collide, then there's a force between them. Okay. So that's the assumption. All right. Anybody remember Newton's second law?
F equals ma.
Not the baby version. F equal to dP by dt. Okay? So F equal to, what this is saying is you have to apply a force on an object to change its momentum. Okay? The rate of change of momentum of an object is equal to the force acting on it. Yeah, that's Newton's second law. Why do we need this? This is the case you need when the mass of a object is changing. F equal to ma is good when the mass of the object does not change. Okay? Remember. Yeah. All right. So now let's. What we're going to do is, so here are these molecules bouncing off the walls. We're going to look at one molecule. Okay. So here's the box, and there's a bunch of molecules in there, and we're going to look at one molecule. And you see, here's the momentum of this molecule, and the momentum change upon colliding with the wall. Why did its momentum change? Because the wall exerted a force on it in this direction. Okay. What changed? You see, the y component of the momentum didn't change. The x component of the momentum changed. And why did it change? Because the wall exerted a force on the molecule. Yep.
Is this subscripted X? I'm sorry, I can't read that. Like for the formulas.
Yeah, x. Yeah. Okay, so the momentum of the molecule changed in the x direction. Well, what is the change in momentum? It's final momentum minus initial momentum. Okay, so since only the x component changed, here's the final x component of the momentum minus the initial x component of the momentum. So there's the change in momentum of the molecule. Over what time did this change happen? Well, the molecule started here on the average, collided, and then it has time to go to the other wall before it will collide again. So that is the time over which that change happened. Okay? And that time is 2d, the size of the box, divided by the x component of the velocity. So that's the time over which the change happened. Okay, so there was the force on the gas molecule, on that single gas molecule. What does Newton's third law say? What does Newton's third law say?
Is that equal and opposite reaction?
Every action has an equal and opposite reaction. If I push down on this table, the table is pushing me up with an equal force. Okay. The wall exerted a force on the molecule. The molecule exerted a force on, again. So this was, okay, this was the force on the gas molecule, and that was the force on the wall. Okay. So the force that the gas molecule exerted on the wall is opposite of that. It's mv square x, mvx square, the x component of the velocity square divided by d. What is the total force on the wall? The force due to all these molecules hitting on the wall. Okay, so let's add up all the molecules. If there are n molecules, the force exerted by all the n molecules. Okay, now every molecule is going with a different speed, you can see that. So what we're going to do is n times the average speed, sort of, okay? So that is the force on that wall. N times mvx square divided by d. Now here is this is the kind of assumptions that go in, okay? So let's look at this. Does the gas, so here you can only see two dimensions, but does it prefer any direction? X, Y, Z? No. So the average speed in any direction is just 1/3 the speed square. Okay. So the force on this wall is nmv square, the bar telling you average, 1/3 of that divided by d. Okay, and the pressure is force divided by area of the wall. Area of the wall is d square. Okay, so force divided by d square, and the d square over there will give you the volume. So let me do that. So pressure on the wall is 1 over d squared times force, and force is n m v squared. Yeah. And the d cube is the volume of the box, so it's 1/3 n divided by volume mv squared. Does this look familiar? Is there, you've seen something like this anywhere? The kinetic energy of the molecule is almost that, except for a factor of half. So let's throw in a factor of half. Okay. So there you go. You have the pressure of the gas expressed in terms of the kinetic energy, average kinetic energy of individual molecules. Yeah. So here's your first big time expression, a macroscopic quantity related to a microscopic quantity. Okay. In just 2 minutes, you calculated something that you measure using a handheld instrument to something that you cannot see. How do you know this is right? You go do experiments. Okay. And see the consequences of this. You can predict the consequences of this expression, and if the gas behaves like predicted, then this must be true. Yeah. All right, so let's make sure that this makes sense. Okay. All right, so here's the temperature, here's the pressure. Okay, how can I increase the pressure of this gas? What can I do to increase the pressure of this gas?
Shrink the volume or add more of the gas.
And add more of the gas, and that would increase the volume, increase the pressure. And added more gas, and that increased the pressure. What did I do in this expression? I added more N, so I increased this number. The volume was the same. I increased N, I increased this number, the pressure increased. You double N, and you double the pressure. That's what Mr. Gay-Lussac's 150 years ago discovered. What else can I do to increase the pressure?
Shrink the volume or increase the temperature.
You increase the temperature. Okay, so if I increase the temperature, what am I doing?
Adding energy to it.
Yeah, what am I doing to the molecules?
Increasing their kinetic.
Speeding them up. Yeah. See, I increased the temperature and I sped up the molecules. Yeah. I sped up the molecules, I increased this term. Okay. So this expression makes sense. Okay. All right, so here's that expression that you derived. All we've done is taken V over there, and then compared to this ideal gas law that you had put together about 50, 60 years ago. If you compare the two, what you end up finding is, here's the kinetic energy expressed in terms of the temperature. So now you have a meaning for the temperature. The temperature of a gas tells you what is the average kinetic energy per molecule that we had talked about before. Okay? You double the temperature of a gas, what you end up doing is you're doubling the average kinetic energy per molecule. So that's what you're doing. Okay? All right, so those are the two main expressions from this chapter. Okay? Again, relating microscopic quantities to macroscopic quantities. Okay, so again, here's the temperature. The temperature gives you the average kinetic energy per molecule. And now you can see that the greater the mass of the molecule, the lower the speed. So here are the speeds at 20 Celsius at this room temperature, at this temperature. If this room was filled with hydrogen gas, the hydrogen gas would be traveling at 2 kilometers a second. It would be going from here to Benares in 1 second. This room is full of oxygen and nitrogen, and these molecules are traveling at 500 meters per second. They're going from here to Riddle in 1 second. Okay, so that's the average speed of the molecules here. Okay, so this is sort of a, so you will see this RMS in a lot of different places. You'll see this in circuits and so on. So what that RMS means is root mean square. Okay, root mean square. Okay, so it's sort of an average speed. The average speed is given by that. This expression is using Boltzmann's constant, and that's the mass of a single molecule, and you can convert that to, you can write it as the gas constant divided by the molar mass. Okay, mass of a mole of the gas. Okay, so anyway, anybody remember? So that's, so these things are useful for the following reason. What is the escape velocity from Earth? Hmm?
11,000 meters per second.
Very good. 11.2 kilometers per second. 11,200 meters per second. Okay. So what did we say our air contained? Okay. Why isn't there helium in our atmosphere? Why isn't there hydrogen in our atmosphere? The reason being, okay, at these temperatures, see, there's the average speed of hydrogen, 2 kilometers a second. Okay, and if you will, so I'm just going to state it. If the average speed is 1/6 the escape velocity, then that molecule will escape into space. So you can go to Publix, buy helium, a helium balloon, and release the helium, and all that helium will eventually escape to space. Okay. So the molecule is light enough, its average speed is large enough where it'll escape from there. Why isn't there any atmosphere in the moon? Because the escape velocity is so low that at the temperatures that you experience on the moon, everything escapes. Okay. So you can tell what the atmospheric content will be of a planet. Jupiter has hydrogen and helium in its atmosphere. Saturn has hydrogen. Why? Because the escape velocity is large, they're far off, they're cold, okay? And the average speed of hydrogen is much less there, okay, at those temperatures. All right, extremely important, equipartition of energy. Okay. When the gas molecule is traveling, is there any preferred direction? No. So the speed on the average should be equal in all directions. Okay, so here's the average kinetic energy, which is 1/2 Vx square, Vy square, Vz square. That's equal to 3/2 kT. We'll write 3 times half kT. So the energy, kinetic energy in the x direction must be 1/2 kT. The kinetic energy in the y direction must be 1/2 kT. The motion along the x direction is 1 degree of freedom. Motion along the y-axis is another degree of freedom. Okay? So the equipartition of energy says each degree of freedom on the average contributes 1/2 kT to the energy of the system. Okay, so very important relationship. So make sure we remember that forever. Each degree of freedom contributes 1/2 kT to the energy. All right. Here's why it's useful. Okay. And by the way, in this expression, temperature is in what units?
Celsius.
Kelvin. Okay. So whenever you see any of these relationship, the temperature is always in Kelvin. Okay. All right. Here's why this thing is useful. Let's say we have a gas in this room. How many molecules? 28. Okay. And what kind of molecules are there?
Nitrogen and oxygen.
nitrogen and oxygen. They're diatomic. Okay, here's one nitrogen, I guess so. So what are the kind of freedoms it has? How many degrees of freedom it has? This molecule can move in the x direction, it can move in the y direction, in the z direction, and anything else can the molecule do. It can spin along this axis, and it can spin along that axis, about that axis. Okay? So it can spin like this, and it can spin like that. So this molecule has 5 degrees of freedom. Okay, let me calculate the total energy of this system and the number of particles. Each particle has F degrees of freedom. Each degree of freedom contributes how much energy to the system? 1/2 kT. See, even I can calculate the total energy of this system. N times F by 2 kT. It's that simple. Yeah. So now if you want to calculate the energy of a system, what does it be? The problem has been reduced to finding out the number of degrees of freedom. Yeah. It's a very useful formula. Okay, so here's a question. What is the average speed of the molecules in this room?
500
Meters per second. So the molecules are traveling at about 500 meters per second. Yeah. Let's say I take a perfume bottle and spray it. Do you smell it immediately? I mean, it should take less than 1 second. Why don't you smell it immediately?
Heavy molecules.
Huh?
Heavy molecules.
All right, so let's give it half a second.
It's gonna push all the other ones out of the way.
So,
They're also not traveling in a straight path.
and there you go, that's it. Okay, so these molecules are colliding a billion times. They're taking the scenic route, okay, not the direct route. All right, so this got traveled this distance, that distance. Okay, so this is the path, this is the distance it traveled before colliding. The average distance it travels before colliding is called the mean free path. Okay? Typically molecules collide 1 billion times per second. The average distance between collisions is that. Okay, so here's the mean free path, and the mean free path. This is the diameter of the molecule. So the bigger the molecule, the more likely it will be colliding. Okay, so if imagine a ping pong ball versus a basketball. Okay, a basketball will collide more. Okay, so the mean free path is inversely proportional to the size square of the ball and inversely proportional to the density. More air molecules there are, more collisions will happen, and the mean free path will be smaller. This is the frequency of collision, how many times it will collide per second. Again, depends on the size. The bigger the molecule, the more collisions will happen. The greater the density, greater the collisions. The faster it's traveling, the greater the collisions. Okay. So those are important numbers. Okay. So here are typical numbers. This is the size of the air molecules. Okay. This is the distance. This is the average distance between molecules. This is the average distance between molecules. You see the average distance is about 10 times the size of the molecule. So the molecules are this size, the average distance between the molecules is this far in the room. The mean free path is 100 times. Okay, so if the molecules are this big, they're this far apart, and they travel the width of the room before they collide. Okay, at these densities. The frequency of collision is about 1 billion times a second. Okay, those are the typical numbers for it. All right, let's take a